Hi, everyone. Hi, Mariana. So our next talk will be online on Zoom and is given by Mariana Clare from ECMWF. And the title is Computer, How Likely is That I Need My Code Tomorrow? Thank you.
So thanks for the introduction. Hi, everyone. I hope you can hear me and see my slides. And also thanks very much for accommodating me on Zoom. Sorry I can't be there in Reading. I've been in that suite many times and I'm jealous of your lunch, but yeah. So today I'm going to be talking to you about how neural networks can be used for probabilistic weather forecasting and also post-processing. So the first part of my talk I did as an internship at the Met Office when I was doing my PhD at Imperial as part of the Maths of Planet Earth CBT, which many of you will know of / are part of. And then the second part is based on the work that I'm starting to do now at ECMWF. So I've got a lot of co-authors on this slide. And I'm based in Bonn rather than the Reading office like Theo. So as I just mentioned, so the first part, I'll be talking about neural networks for probabilistic weather forecasting. And this work was published in QJRMS last year. So you can check it all out there. And there's also code available. There's a link in that paper if you want to check it out. And in the second part, I'll start is very much ongoing work about the using machine learning techniques for post-processing. So part one. So before I sort of start talking about neural networks and sort of looking at results, I want to briefly talk about the data set that I'm using. And so I'm using this data set, which some of you may have heard of, called WeatherBench, which is a benchmark data set established by Stefan Rasp and co-authors in their 2020 paper. And it's basically ERA5 reanalysis data set regridded onto a very coarse resolution. So it's only 32 by 64 grid points. And so they've done this for a series of input data variables, which I've listed on the slide here. But it's all available through this GitHub link, which I put on the bottom right-hand corner. And you can go there and download the data, and you don't have to go through Copernicus or anything like that. So it's all readily available. And so the idea of this is that you kind of create a benchmark where everyone can run their models against it. And we can easily compare sort of which models do better in some areas and which models do better in other areas. So obviously to do that, you have to have like a target, like a competition almost, if you like. And so the target that is set by WeatherBench is to try and predict the geopotential at 500 hectopascals, which are referred to as Z500 throughout probably, and temperature at 850 hectopascals, which is I'll probably refer to as T850. And we do this for the 3-day and 5-day lead times. And what you see on the screen here is just two examples of the 3-day forecast for Z500 and T850, just to show you that it really is quite coarse, and you can kind of see in the plots it's sort of very granular. And in the plot on the left, because the 500 hectopascals is that much further up in the atmosphere, you really can't see any sort of like land-sea distinction. On the one on the right, you can possibly see it. If you stare long enough at these plots, you can convince yourself. But really, we're talking very sort of, especially with Z500, sort of we're not doing like surface predictions. That's all I'm trying to say. So that was a very brief look at the data set. And now I want to sort of introduce neural networks. So I don't know how many of you will be familiar with a neural network, but if you're very familiar, you can sit back for this bit, but I just wanted to give a very brief introduction. So what you have on your screen is possibly the simplest neural network that you could have. So you have an input layer with 2 inputs. You have one hidden layer, which I'll come back to, and you have your output layer. And all this neural network is trying to do is basically train the weights and biases, so the weights are the WIs and the biases are the BIs, to minimize some sort of loss function. And in this work, we just use a simple mean squared error loss function. And so this is sort of the simplest format you could have, but obviously neural networks can be very, very complex. So the way they can be made more complex is sort of having more hidden layers, having more nodes in the layers, having different architectures. And I'll briefly introduce one of those more complex architectures later. But really, when it comes down to it, this is what a neural network is doing. The other slight complexity of a neural network is that you have these activation functions on the nodes. And those work just like what they say on the tin, really. So it's a function which evaluates, say, a weighted sum. So in this case, W1x1 plus W2x2, and chooses how much of that weighted sum gets passed forward onto the next node or the next layer. And in this work, we use the ReLU function. I don't know if you can see my mouse, but if not, it's just the activation function in the top right-hand corner. And basically what this means is that if in this particular example, if W1x1 plus W2x2 is negative, then nothing gets passed forward. So I like to think of it as like, you know, those games you played with the kids with like lights switching on and off as different things are activated. So it's sort of working like that. So that's a very basic structure of a neural network. The other thing I'd like you to notice is that in this very simple neural network structure, you only have one output. So you have a deterministic output rather than a probabilistic one. And as was very nicely introduced by Romain this morning, and then various other authors, other speakers, and in weather prediction, uncertainty is very important, and having some sort of probabilistic output is very important. So I wanted to try, in this work, we wanted to try and create some sort of probabilistic forecast with a neural network. And actually, probabilistic forecasts do sort of exist as sort of standard with a neural network if you have a classification problem. So those are those sort of standard problems that you might have seen where you have given something some images and it has to class the image, whether it's a cat or a dog or a horse or whatever, and that's a classification problem. And so what we did was we decided to turn essentially what was a regression problem into a classification problem by just binning the data. And so we binned it into 100 groups and they're all of equal width. Since then, I've had some thoughts about this, and potentially we could at a later date bin it just for the extreme values, or bin it if we're mainly interested in like a certain region of temperature, we could do lots and lots of very narrow bins around there and sort of wider bins in areas that we're not interested. So there's definitely more you can do with this concept. And I'm just showing the distribution of the bins on these plots here, just to show you how skewed, just to remind you how skewed geopotential and temperature can be, are. So you see that you have, we tend to like sort of nice Gaussian distributions, and this definitely isn't Gaussian. So by using that categorical data approach rather than a regression approach, it allows us to use this layer in sort of the standard layers in neural networks called a softmax layer. And what you see here is two example outputs of a softmax layer. And on the right, actually to me, this is the less interesting figure. What happens on the right is that the neural network has correctly predicted the correct bin. So great, okay, but there's no advantage then to having a probabilistic one. If it had just been deterministic, we'd have just got the correct answer. What is much more interesting to me is the graph on the left, which shows where, so the neural network has predicted the incorrect bin, but it's shown the real bin still has a very high probability of occurring. And from a meteorology perspective, that's way more interesting, because it means, okay, if it had just been deterministic, it would have just told me whatever bin this is, 50, whatever, and I'd have had no more information. But now with my probabilistic, let's say that the real bin is actually some sort of extreme event. As a meteorologist, you can still look in and be like, okay, so it's probably going to be 50, but I've got this high probability of this extreme event occurring. So for me, the figure on the left is actually way more, is a way better example of what converting to a probabilistic forecast can do for you. So this is not the first time that people have tried to use predict probabilistic output from a neural network for weather. It's one of the first times that we've done it with just a single run. So normally what people do is they train an ensemble, or they try and predict, they have to train the model various times, or they have to do inference multiple times. Whereas our approach requires just a single run, and you produce a full probability density function for every point in time and space. So it's much more computationally efficient. The other layer I wanted to talk about in neural network, sort of another special layer, is the convolution layer. So if you like this problem of WeatherBench of input data, so you saw those input variables that I have, like, I don't know, just a relative humidity, temperature at various pressure levels, etc. And then you're trying to predict a forecast, make a forecast. That's really just an image-to-image problem. And so what you can use, which a lot of people do image-to-image problems in machine learning, and they tend to use these things called convolution layers, which just take a convolution and they pick out important things, or features of interest, perhaps a better way to phrase it. So in this case, if you use this kernel, you pick out the edges, which you can imagine for a weather forecasting problem might be interesting to pick out the edges of a front or something like that, and then it can help the neural network predict what's going to happen next. And so this is what we use in our network. The hidden layers, if you might remember from our very simple schematic, they're not actually like what I showed you, they're these convolutional layers. And so that brings us to the actual, what the network looks like. And so you can see, like I just mentioned, these convolutional layers, the softmax layer, and there are some other layers going on which I'm happy to talk about afterwards. But the key point here that I want you to take away is that, so we don't actually use, we try and use a slightly more complex structure than what I showed you in the simple schematic, which is this residual neural network. And actually, this residual neural network scheme is quite similar to the idea of a forward Euler finite difference scheme from an NWP model, if you're familiar. And why do I say that? Well, because you have your x that comes in, you do some operations to it, and you get your f of x, and then you bring back in your x, which is from before, with this identity connection. And so it's kind of similar to what goes on in a forward Euler. And the reason that people do this in machine learning is because if you have more and more layers, the network you're getting further and further away from the input, and you can start getting issues of, basically in simple terms, the neural network's getting lost in its own layers, if you like. And so what this identity does is it brings back in the previous state. And so the network has a little bit more of an idea of where it is, basically. And the final bit of architecture, I promised before we look at some results, is, so the WeatherBench data set, you may have noticed, is absolutely huge. It's got a lot of variables. And so we did, you can read about this in our paper, we did some sort of feature importance selection and tried to really scale it down to really only the variables that are important. But even so, we still got a training data set of 36 variables with, and that's, so each pressure level, I'm considering that as a variable. So that's basically 36 pressure levels of different, different specific humidity or potential vorticity or whatever. And unfortunately, so I did this internship during lockdown. And so all I had available to me was, I didn't have the Met Office computational power available. All I had was what Imperial had on the supercomputer, which was a little bit limited. And so I couldn't train on all 36 variables at the same time. And just to give you context, the Stefan Rasp paper, they trained on 117 variables. So it's not like we had a much bigger data set than anyone else. It was just, the computational power that was provided to us, that was available to us. And so what we decided to do was, instead of training one ResNet, we trained lots of individual ResNets on each variable, basically. And then we used this approach called a stacked neural network to combine the outputs to get out one final probability density function. And this stacked neural network really is just basically learning how to weight the outputs from each ResNet, basically. So how to weight the outputs from the geopotential, how to weight the outputs from the temperature, et cetera, et cetera. So this is really just an example of where we had to sort of think of a new method because we didn't have the computational resources that we would have liked. So now to show some results, which hopefully is the more interesting part. So I just wanted to show you an actual concrete example first. So this was Storm Ophelia that hit the coast of the UK and northern France in October 2017. And so on the top plot, you see the deviation from the climatology for Z500, and you can see the storm. I mean, this also serves to show you how coarse resolution we're dealing with is, but you can definitely see this sort of storm patch coming in. And then on the bottom left, you see the 3-day forecast. So on the 3-day forecast, it's done a very good job, I think, here in sort of the area to the east of the US and Canada. It's done a not so great job in Greenland, but you can definitely see that a storm is coming. And then in the 5-day forecast, as you'd expect, the results are again worse. Again, Greenland is not great. And maybe some other parts of the plot aren't as good as the 3-day forecast, but that's what we would, we'd expect that a 5-day forecast would get worse. But hopefully even the 5-day forecast, you could argue that you can see that there's a storm coming in, which is what we need to know. So that was sort of like a specific example, but one of the advantages of WeatherBench is that you have, so lots of people have run different models on this data set, and so you have errors that you can compare with. And so our results are the top row, the stacked neural network. Then for persistence, so we're happily beating persistence, we're happily beating climatology. We're also happily beating the IFS T42, so obviously IFS at a much coarser resolution. And we're sort of the same order of magnitude as this Wayne et al. Paper from 2020. But the thing to note is this Wayne et al. Paper, they use a more complex neural network, and they don't have a probabilistic aspect. So they're just predicting deterministic. Raspberry in 2020, yeah, they get much better, but they're using 117 input variables because they had a computer with a terabyte of memory, and we're having to use 36, and even then, make some adaptations. So it's not surprising that they beat us. And then luckily for ECMWF, operational IFS is still much better. So again, not surprising. But we're sort of in the same order as some more complex neural network methods. So I keep on harping on about probabilistic forecast and why it's important. So this is just two examples. This is just an example of what you can do when you have a probabilistic forecast. And so you can construct these spaghetti plots. And basically you can see, so if we take a point, let's say we take a point in the UK, we can see that the probability that the temperature is less than 273 degrees, and over Reading is 10%. And then we can take another point, the probability, for example, over northern Greenland, that the temperature is less than 263 degrees is 90%. And so we've got these probabilities basically for temperature. But the other thing that these plots give us is, so when the lines are very, very bunched up together and when they overlap, that's where the neural network is saying, okay, yeah, I've given you a result, but I'm very uncertain about my result here. And in particular, you see that if you compare the 3-day forecast to the 5-day forecast, the lines get much, much more bunched up together. And there's even points where they start to overlap. For example, here over northern Norway, where the distribution for the 263.15 Kelvin and 273.15 Kelvin is starting to overlap. And so, yeah, basically this is saying, the neural network saying, I'm very uncertain about what's going on here, which I think is useful for sort of from a scientific point of view, rather than just having a deterministic output where you have no idea how confident the network is. And also, so we've seen a lot of CRPSs this morning, but we can also work out the CRPS. And so we compared it with this Cher and Missouri paper, who did an ensemble approach for Z500. And so strangely, we have a much better CRPS for 3 days than we do for 5 days. And then for T850, okay, yeah, we're not as good as the operational IFS or even the Dressed era scores, but we're sort of in the same order for temperature. So that's a nice result. But ultimately, the neural network is doing worse than operational models, which is maybe not surprising because, these operational models have been developed for years, for decades even. And so what I'm working on now at ECMWF is really how to combine NWP models with machine learning techniques and use them together to end up with an improved result. And so this is part 2 of my talk. So specifically at the moment, I'm looking at how we can predict 2-meter temperature, global bias and 2-meter temperature. And I'm defining that global bias to be equal to the operational forecast at a lead time of 10 days minus the operational analysis. And on the left-hand side, you see what the real bias looks like for 2017, averaged over the whole year. So I'm actually doing a prediction per day, but just for now, obviously I can't show you 365 plots, so I've done the temporal average. But even in the temporal average, you can see some structures coming up that you might recognize, like this positive bias here, and negative biases in Africa. So these are sort of like known phenomenon. And sort of to have a good benchmark, I didn't launch straight into using a neural network. So instead I thought, okay, so what can we do if we just do like a simple moving average approach? Or better still, okay, how about if I use the bias from yesterday's forecast on today's forecast? What does that do to my forecast error? And so that's what you can see. It's the leftmost point on the right-hand plot. You see that the error, if you just use the bias from yesterday on today's forecast, you see that the error is very, very high. It's much, much higher than the raw forecast error. So okay, let's be a bit more, do a bit more then. Let's take an average of 2 days ago's bias and yesterday's bias and add that on to the raw forecast and see what that does to the forecast error. And we keep going and we see that the error, that causes the error to go down. And eventually when we if we take the average of the last 60 days and add it onto today's forecast, we can beat the raw forecast error. And then sort of 120, it gets a bit better, and then it starts going back up again. And so this one at 120 is now sort of our new benchmark to aim for. So if we can't get the neural network to do better than that, well, we just pack up and go home, really, because we just use a moving average and we do great. So now we start looking at neural networks, and specifically we're looking at MLPs, for those of you who know about neural networks. But for those of you who don't, that very simple schematic that I showed at the beginning, that's basically an MLP. And so on the left-hand side, again, we have the real bias. Now on the right-hand side, the top figure is if we just give the neural network latitude and longitude and we say, okay, predict the bias for me. And you can see that it's spotting this diamond shape, which you can definitely see in the real bias average. Or at least I think you can definitely see it. And then next we gave it orography and land sea mask. And you can see that it's spotting like this negative bias over Africa and the positive bias in sort of northern regions of Canada. And the good thing about these bias plots is if we add them onto the raw forecast, we get a better forecast error than if we just using the raw forecast. So that's good. That shows that we're doing improvements. So these are sort of what you could call state-independent variables. And so if we add in state-dependent variables, so now we've given the neural network all of the vectors from the bottom one, plus the 2-meter temperature, for the forecast for the 2-meter temperature. And you can see that the pattern is much better, although there are regions where it's definitely getting it wrong. Like in the Southern Pacific, it's very wrong. In fact, in pretty much all of the Pacific, it's just not doing great. And so, and actually, if you add on this bias to the raw forecast, you get a worse forecast error. So this is really what I'm working on now, trying to understand what is going on here, maybe which better neural network architectures to use or better input data. So I'm happy for any suggestions that anybody has for things that I can try. And so that sort of concludes this sort of whistle-stop tour of using neural networks for weather forecasting. And I hope I've convinced you that they can be a useful asset and they can be combined with existing NWP models. And I'll leave you to read the rest of the conclusions. So thanks very much for listening.
Thank you very much, Mariana. So I will try to use the microphone. Are there questions in the audience?
The microphone for the online session is here, so either use this one and hopefully this one pick it up, or come to the front.
Let's see if you can hear the question.
Hello, Olivia. So I have two questions, pretty simple. So you say that you want to calculate a bias, you add it to the forecast and reduce the forecast error. How do you add it to the forecast?
So I just do. Oh, I can hear myself. So basically, I take the forecast and I do forecast. So the bias. Well, so actually, sorry, I think it might be subtract with the formula. Just let me have a look at the formula. But basically, I can't remember if I do forecast plus bias or forecast minus bias. And then I take that and subtract it out.
Sorry, say it again.
Can you say it again? Sorry.
Yeah, sorry. Sorry, I wasn't being very clear. So I take the forecast and I add on the bias, and that's my new forecast.
Yeah, but what lead time during the integration of the model?
Sorry, so I only have one lead time in these models, so I just have the 10-day lead time.
Okay, so there's one point. And the second question, when you do your neural network, do you train, so I understand, do you train each variable independently? And then you add on to that variable, or do you take into account the correlation between the variables?
So is this is for the first part of the talk, do you mean?
No, for the second part of the talk, when then you add it on you calculate the bias to...
So I'm just training it. So I just give it all the input data. So at each stage that you saw, I start again. So I just give it all the input data in one go and then train again. So that all of the neural networks are independent, but they should learn. That's something that the neural network should be able to do, is learn the correlations between any inputs.
Yeah.
Are there further questions?
Hi, Mariana. Just one very short question on the first part, right? So when you're stacking and independently, are there any benefits in terms of interpretability?
I didn't hear the last part, sorry.
So apart from computational, let's say, scaling,
sorry, apart from computational scaling, what was the second part? I can't hear anyone, sorry. I don't know what happened. No. I think your sound went. It just suddenly stopped working. Yes, can you hear me? Shall I answer typing? I don't know. Okay, I'll answer yes. Oh, good. Yes, it's not just me. I don't know what happened. So I can answer. So yes, there's definitely advantages in interpretability. because what you can do is the stacked neural network is very, very simple. So you can see which weights it's learned. And so you can see, for example, that the ResNet that's trained on the temperature is more important than the ResNet that's trained on, let's say, some constants. Does that, I don't know if you guys can hear me or not. Okay, cool. Oh.
Is it back now?
Yeah, it's back now.
Ah, it's back.
Maybe we can.
So I was suggesting to thank you. And
I hope I answered the question. The answer was yes.
Yeah, let me ask you one short question. So about the training of the neural network in the first application. So you're using softmax outputs, but what about the loss function? Do you use simply multi-tap classification loss or something different? Okay.
Yeah, so I'm just using categorical entropy.
Because this loss does not take into account that if you predict just the next bin, it's better than predicting a further bin, and so the classification loss function does not really take into account the quantitative aspect of the variable.
Yeah, so I think I think now, so I've since done some more work, and I've done an approach where I use a Bayesian neural network instead, and you're using a KL, what's it called, the KL divergence function, where you're trying to match up the distribution. So I think if I did it again, I would use a loss function like that. But in this work, I use that approach, which definitely has some limitations. I completely agree.
And also, I was wondering whether it would make some difference to have like more, so bins that wouldn't be all of the same size, but more of the same population size, like quantile of the climatology. So do you think it would make any difference, or maybe not so much?
I mean, I guess it depends what the problem that you're trying to solve. If if you want to, I mean, yes, the answer to your question is yes. If you made them uniform by population, then you would get sort of maybe a better result, because it's known that if the classes are like equally distributed, you can get better predictions. I guess for my problem, I was just trying to really do like global temperature prediction. And so maybe in the Arctic, knowing that the temperature was going to be between like, I don't know, -40 and 0 is not that useful. You really want, so that's why I did it just by width, trying to keep the granular level. But this approach, yeah, it totally works. You can now sort of, if you go and look at my code, you can set the bins yourself. And so if you were like, okay, actually, I'm more interested in the classes having equal size, or I'm more interested in this particular part of the range, and I'm just happy to bin everything else in the other group in another bin, then yeah, you can totally do that.
Okay, thank you. So maybe that now it's working. One last question in the audience. Yes?
I have one question. Are the prediction results sensitive to the bins, the choice of the bins initially? Because they are from the beginning, right? If I understand well.
Well, so one way that they're sensitive immediately is that, for example, let's say the bins, if I made a really wide bin, then my results would be 100% accurate. So yeah, there is definitely like a sliding scale. So, and if I made an infinitely small bin, then it's back to the continuous problem. So yes, definitely it will make a difference. We decided that this 1 degree Kelvin, or 100 meters squared per second squared, was like a good, it made sense to like meteorologically, like knowing within that bin. But yes, I could definitely have manipulated my results by just being like, hey, everything's in one bin, I've got 100% accuracy, guys. Yeah, that's a great question.
And don't you constrain also your prediction out of sample, the value in the out of sample setting Aren't they kind of like constrained by the way you have defined your bins initially also?
Yes, yes,
right?
That's true. Yeah.
Not be able to go too far out.
Yeah. I guess we thought that just because it was like we took literally the bin dip from 1979 to 2019, that would, and we were dealing with a global problem at a coarse resolution, that would be enough. We would capture, we wouldn't have too many out of sample ones. But yes, that's obviously completely right as well.
Okay, thanks.
Okay, thank you very much.